This is Data Analysis with R for Educators. I'm Christopher Cameron. I'm co-presenting today with Wilbur Uma. I'm going to paste some links in chat if you're just joining us. This is a link to our material and also a link to the RStudio login to make sure that's working for you. We'll do our demos today in RStudio Cloud so we can demo that platform. It's a convenient way to distribute materials to people who may not have R installed. So I'm going to put up some polls to start with. We'd like to know a little bit about your background. Okay, good mix of teaching and research. A lot of people have used R before. If you haven't used R before, that's okay. We're going to go over some R basics to start off with, so the demos will make sense. A lot of Python users, that's to be expected. I'll point out some differences between R and Python that may trip you up as you're transitioning to R. Python and R are complementary tools. It's good to learn about both of them. Let's see, what are you guys using already? A lot of R, a lot of Python, and some of the popular ones in there. And a lot of votes for Excel. This was in last time, a lot of people using Excel. If you're using Excel for data analysis, R is a great next step. All right, well, thank you. This helps me. I'll try to target the presentation a little bit to your backgrounds. I'm going to paste some links in the chat. These are direct links to the PDFs. We got 3 different PDFs. One is our slide deck for today. One is a resource sheet. It has some of the resources we mentioned in the slides and a few extra links, some information about R programming, if that's what you're interested in, and R for data science books that are free ebooks. And finally, some people last time were interested in how we set up this cloud demo. So I put together directions for how I put together this cloud demo environment and how I synced files into it and how I updated it. So those PDFs are available for you on the GitHub. So today, at the end of today, I'd like you to know what R is. What is R? How does it fit into the data science ecosystem? Is it a good choice for your data analysis? What features make R useful for educators, and where you can go to get more information? It takes time to learn R, and this could be your first step. And the materials and demonstrations today will help you decide if R is worth the investment. So our agenda today, I'm going to go through an R orientation, about 20 minutes, then look at some of the R software, and then we'll do demos for the rest of it. The demos are all in blue. So R is good for tabular data. If you have vectors, if you have lists, if you have spreadsheets, kinds of data, that's a good use case for R. R is good for statistical analysis. It is good for data visualization, and it is good for integrating custom code that you may have written in another language for a specialized type of analysis into a statistics ecosystem to make it easier to use. R is less suitable for unstructured data, file system scripting, and this is debatable, but I would say less good for data scraping, cleaning and formatting. There are packages that make these things possible. Some people want R to do everything, so that you can get packages to do these. A more general language may be a little easier, though, if that's your main use for a scripting language. So considering the statistics software ecosystem, you can see that R here in blue is a relative newcomer to statistical software. Many of the major statistical packages were developed a long time ago when computers really generated a lot of output. You would run a program and you get printed output. That model persists today in some of these software programs. R was written in a more modern time when we were thinking about object-oriented programming and things living in memory and being more interactive. So R operates with a different philosophy than some of the earlier statistical programs. You can see R and Python started about the same time. This is also at the time of Java, when object-oriented programming was very, very much it was the way to do programming at the time. I've also highlighted on here a new platform called Julia. That's a language that's trying to combine the best elements of R and Python and MATLAB. It may be in, I don't know, maybe 10 years, we could be having talking about how you could use Julia instead of R and Python. I highlighted R, Julia, and Python because these are three modern open source languages that are favored by data scientists. In that people often use all of them, all three of them, or two of them. R and Python have significant overlap and similarity. Python is a more general language. Python tends to be favored for deep learning. R and Python are both very popular for machine learning. R tends to be favored for statistical analysis. But both R and Python have huge communities and many, many add-on packages that make them a great choice for research. You can make them do almost anything through the add-on packages. Julia is an exciting general purpose language. It's designed at MIT with numerical computing. It's pretty new project, so it's only recently got to version 1.0. It's supposed to be more performant than either R or Python or MATLAB, but it still has a small ecosystem compared to R. Something to keep an eye on. But when you're thinking today, what language should I learn? R and Python are probably your best bets, and R is a great choice if you are a researcher who does statistical analysis. It's a great first place to start. This is a question that just popped up. In my opinion, Python would be more suitable for data scraping than R. Yeah, other people may feel differently. I actually linked to some in the resources sheet. I linked to Chris Bale's research. He uses R for everything. He does a tremendous amount of data scraping in R, scraping Facebook groups and other web-based data. Hadley Wickham created a large number of packages, some of them to help address the shortcomings in R with respect to data scraping. So you can make it work. And if R is the language you know, and you want to be able to do scraping in R, there are ways to do it. I think it's a little easier in a more general language like Python, but that's, I'd say, largely opinion. It is possible in R. So R came about because two faculty members wanted a better software environment for their teaching laboratory. They did not like the commercial offerings available, but they did like some features of this statistical programming language. But they also wish that it behaved differently. They wish it had some modern language features that they had seen in Lisp. And so when R developed, it was an S implementation with some features that they liked from another language thrown in. And then they distributed it via the email list. And a few years later, a colleague persuaded them to open source R. And that's how that's the story of R, and that beginning of, we don't have the tools that we really want. We like some things about this language. We wish it had features from this other language. Let's put them together and then make that available for other people to work on too. That's the core of R, and it explains a lot about how R came to be the way it is. R has collective and eclectic development. It means that R's developers will borrow code conventions and programming styles freely. You'll see a mix of conventions when you look at R code. It also means that because different people want R to work different ways, you'll probably find that there's many different ways to accomplish any particular task in R. You'll do some research, maybe you'll Google about how to do something in R, and you'll find two different sources. They'll be contradictory, but they'll both be true because that's how R works. R is focused on practical, productive use. And because of its flexibility as a language, you can write packages that make R appear to be a certain way. And it is not actually that way under the hood. It's just acting as if it's that way. It's easy to come up with some misconceptions about how R really works under the hood just by observing how packages work. We'll talk about a few of those things as we go on. But in general, R is made to be very usable and very productive. But you may get some misintuitions about how it works under the hood, just based on how packages behave. R is used and supported by a community of mostly academic researchers, and more recently data scientists and the companies that employ them. So it gets its power, its new features through these packages that are developed by people in the community. There's over 10,000 add-on libraries for R. And these packages can target either highly specialized research areas, or they can be used to share and implement cutting edge methodology. If you're writing a grant and you have a part of the grant is about developing, making your methodology accessible to the research community, making an R package is a great strategy. If you need help making an R package, talk to your local advanced computing center. I know we do that at the Center for Advanced Computing at Cornell. You can hire us to help you package up your R code. So the official package collection for R is at CRAN. This is the most highly vetted collection of packages. That's probably where you'll go for most things. If you're in a specialized subfield like bioinformatics, there may be a specialized repository just for your packages. So Bioconductor is a big repository for bioinformatics packages. It's also possible to distribute your packages directly from GitHub. So you would put together your code, bundle as a package, and then people can load your package directly from GitHub into their R. In addition to this community that uses and develops for R, there's also this active community generating tutorials and demos. RBloggers is a great aggregator for pulling together demos generated from all different sources. RStudio has pretty good materials for learning how to use R. And we have our own CVW. Cornell Virtual Workshop has their own module in R that's a free self-paced introduction to R. It covers some materials we won't cover today, like using R in the cloud or in the clusters, and using R on multiple cores. Aside from the community is a great feature of R. The documentation in R is another wonderful feature. It has good built-in help and documentation. When you look at the help entries, it'll have a description of each function and their arguments. It'll have examples that show you how to use it, and it'll have references to the manuals or academic papers that describe the methods that these functions are implementing. So it'll usually be a statistics paper about a sampling method or about an estimation method. You can learn a lot about the underlying statistics going through the R documentation. For packages, you usually get a few extra things. When you get someone else's package, they usually put together a vignette that demonstrates how you can use the package to perform an analysis. So it'll start with data. It'll talk you through what they're trying to use the data to discover. It'll show you how they use the methods, usually generate some plots. It's like a whole start to finish. Here's how you use the package to do some analysis. It's a wonderful way to learn about a new package. Usually these packages will also include a bundled data set that supports that vignette. And it also demonstrates the required data formats. One of the things about R is that packages work well with the data formats they expect, and they work unpredictably with data formats they don't expect. So being able to inspect the expected data format is very helpful when you're trying to learn how to use a new package. Base R is a command line interface that you interact with through the R console. It's free, runs on a variety of platforms. It's interactive. R is interactive, but in a different sense than we would usually apply that word. It's interactive in the sense that you make objects and they go into memory and then they live there, and you can query those objects and you can manipulate them and you can apply new functions to them. So when you do an analysis, you can sort of keep working with it. It doesn't print out a bunch of output onto the console. You can apply a sequence of steps and you can explore as your curiosity drives you. When most people using R are not using this R console directly, they usually use it through an interface that wraps that R environment. Today, we're going to look at the RStudio IDE. Jupyter Lab Notebooks is another great choice. You can also do this through Google Colab if you want a cloud-based solution. Someone asked last time, why aren't we teaching this in Jupyter Lab Notebooks? It's because the setup is a little harder. I personally use Jupyter Lab Notebooks for R. I like its clean interface. I think RStudio is a little claustrophobic, but RStudio is a very popular choice. When you're in classes teaching that where you're learning R, you're probably going to be using RStudio. When you're looking at tutorials, they're probably using RStudio. So it's a good place to start until you're comfortable with R and ready to look at it in a different interface. If you already use Jupyter Notebook, just install the Jupyter kernel for Jupyter Notebook. I put directions in the resource PDF about how you can do that install. Here's the R console. It's pretty basic. It's a text-based console with a prompt. You type commands and results appear below, just like they would in a normal terminal-based program. Mostly, as I said, people don't use that directly. Mostly people are using something like RStudio, which is a development environment that goes around R. R, just a tip, if you're going to install this on your own computer, first you install R, then you install RStudio. RStudio doesn't include R inside of it. It uses your installed version of R. Today, we're going to be using RStudio Cloud. It's a hosted version of RStudio. It has the same interface as the desktop application. They did a really good job matching the desktop and the cloud versions. So the stuff you learned today is directly applicable to your local install. Here's the RStudio interface. You'll recognize, here's the console. It's down here. It's one of the quadrants, has the console, but there are a ton of other tabs, more tabs than anyone ever needs available to do all kinds of different things. We'll talk about some of those today. So today, we'll start a quick demo. We're going to be using an RStudio workspace. I'm going to paste this into chat. The directions for how to make and share an RStudio workspace are available as a PDF in the GitHub. So you should be able to click this link and it will load an RStudio project. You will need to log in. The project will start up. It'll take a few minutes it'll say starting up. Once it's done, could you raise your hand? Use the raise hand button and then I'll watch for a lot of hands being up. Thank you. Okay, I'm going to put everyone's hand down, and now I'd like you to raise your hand if this is not working for you, so we can help debug it. So if you're having trouble, please raise your hand. If you don't see what I'm sharing on the screen, if your own screen doesn't look very similar to what I have on my screen, let us know. In the meantime, I'm going to open a file here. It's called 10minutes2.r. It's in the Files tab. Okay. One quadrant has a Files tab. If you click it, you'll see a list of files that are in this project. Looks like when sorted by name, it's reverse sorted by name. They're all sorted by name. It's pretty close to the top. 10 minutes to R is our first file. It has some directions to follow to get your environment set up so it matches mine. It means clicking in the upper right quadrant, look for the environment tab and click it. You shouldn't have anything in there. So your environment should be empty. I'm going to click on the Files tab so you can find this file. And click back on the Console tab after you've opened the file. And you should have a blinking cursor here. Great. All right, just so what we're looking at here is an R script file. You could create an R script file by using this button under here. You can say make a new R script. If you wanted to make your own, that's how you do it. I've already made this one, so you don't have to do that step. In an R script file, it is essentially a list of R commands and comments. So comments look like this. They start with a pound or hash symbol. You can put comments after a command, but you cannot put comment before a command. If you try that, the command becomes part of the comment. So I have my R screen been pretty small so that it looks large to you. Normally, I would make the window much larger when I was using it. It helps with that claustrophobic feeling. But in order to make the text legible, we're going to use it in this small mode. I recommend you make yours as large as you can. So just to start off, R is a calculator. You can enter some arithmetic, 2 + 2, press return. That will print out the result on the next line. This is the essence of the R command line. Some things to note. There's an order of operations. Is the standard one. You can use parentheses to group if you need to change the order of operations. R is for numerical computing. That means it's convenient for it'll automatically use floating point when you divide two integers. It's not going to be, the answer is not 1 like it would be in a more general programming language. Instead, the answer is 1.6. That's important because we're using R to do statistics and math, and so this is the behavior we want, and this is the behavior it has. A few operators you might not be used to. If you're already used to Python, you can use the double asterisk for exponentiation. You can also use the up caret. The modulus and integer division operators are probably the only ones you may not have seen it before. In R, this is how they're defined. R also has a set of logical operators. The less than, greater than, less than or equal to, all these you probably are familiar with. For comparison, in R, it's use a double equal sign, just like in Python, if you want to know if two values are equal to each other. In R, you use an exclamation point for not, so this is not equal. This is same as in Python. You can negate a value by doing not X. The operators here that you may not be used, these are bitwise and or and. So if you put in a list of true and false values, if you have two lists of true and false values, it will compare them pairwise and give you a vector of results. So go ahead and try. Scripts are supposed to make it easier so you don't have to type so much. So when you have a script file written and you want to run a line out of it, you can put your cursor somewhere in this line. And hold on a second. So you put your cursor somewhere in this line, and then you click the run button here on the console. If you mouse over this run button, you'll see a message pop up, and it shows you a key combination you can type to accomplish the same thing. So in my case, it says I can type command return. It could, if you're running on Windows, it's probably control return. But either way, you can use that to run one line at a time through a script file. And let's see, someone's having trouble getting the files. Make sure you're opening up the 10 minutes to R. No, I can check it though. There. All right. In this file, if you're having trouble loading this file, yeah, first of all, make sure you have this RStudio Cloud project, that it has this ID number up here. Then click on the Files tab and look for this file called 10 minutes to R. Great. Okay. addition to all logical comparisons, there are a variety of math and statistics functions built into R. If you haven't programmed before, or if you've used another program, if you use SAS or Stata, this way of calling a function may look weird. When you call a function, use the name of the function is the part outside of the parentheses. The arguments to the function go inside the parentheses. In Stata and in SAS, I believe you type the function name, a space, and then the argument. So it's essentially the same idea, but it looks slightly different. If you're already using Python, this looks exactly the same. So at this point, I want to switch over to an R notebook. You've seen what an R script looks like. You've seen its options for communicating. So I have commands and I have comments. It's perhaps not ideal for teaching. You see that for starters, I have to constantly switch my attention between what's going on in the script and the output down below in the console. The comments are not visually interesting, and really neither are the commands. Everything is the same, one of two colors. Because I have limited space for comments, my explanations are stunted. And you don't really know what's the structure of this document. Where is it going to be? What's the point of it? You can't tell any of that from looking at a script file. So we're switching over to 20 minutes to R. It's the file that ends in RMD. It stands for R Markdown. So it's this one. And to make it easier to read, I'm going to grab this bar right between console and the text and lower it. You won't have to do this if you have your screen larger. This is an R notebook. It's a different way of presenting information in R, tracking information in R, and using R. So instead of writing a script file, now we can use this other format, this notebook format. And in a notebook format, instead of everything being code with some comments on the side, in a notebook, everything is text, and code appears in special blocks. It supports a style of documenting your analysis called literate statistical analysis, where you get to mix your documentation and your explanation and your interpretation and your code in a single document. So you can present your narrative, your analysis in a more narrative format. So once you open this file, you should click on this visual button. That will render it for you nicely. In the visual mode, there are normal text formatting tools that you're familiar with from other word processors. So you can bold text and italicize it, put it in code marks. So underneath, what's powering this formatting underneath is something called Markdown. This is R's version of Markdown. It supports a variety of text formats. It also supports LaTeX equations. You can do bibliographies as well. It supports headers, and those headers, if you use them, will make an automatic outline that shows the structure of the document, so you know where we are and you know what's in it. So R as a calculator, for instance, is one of the headers. You can see it right over here on the sidebar. That came out automatically just because I labeled it a header. You've seen this content before, but here it is in Markdown format, where I could format. So I could have my list of operators. Now they're really a list. Now I can put the operators themselves in code format. I can emphasize the list titles. It's at least more visually varied and hopefully also more visually interesting. Code appears in its own block. So here's our 2+2 again. I could run this by clicking this run button in this that's for this little gray box. This gray box holds some code. This is the run button. It applies to the whole gray box. The answer appears right below it inside the document. So I no longer have to switch between console and RMark and the script. Now I have my code and its output, and they're paired together right in the document. So I can actually minimize this console by clicking the minimize button. Get a little more space to look at my document. Drag this over a little bit as well. All right. So I'll scroll back to where we were. We were down here looking at functions. I want to mention that you don't need to program functions to use R, but you do need to call functions. Applying functions to data is the fundamental building block of statistical analysis in R. And to emphasize, here's the form of calling a function in R is to you call the function name and then you include arguments. There's multiple arguments, you separate them with commas. Here's an example, here's log 10. There's another version of log that takes two arguments. Any idea what that might do? You could think about it a moment. You don't have to answer. Just notice are you sure that you know what this does? We could check into that by looking at the documentation. You start the question mark. You put a question mark in front of the name of the function. That will bring up the help. I'll run that. You see the help tab highlighted. It brings up the help for log. You can scroll down and look for the version of log that requires two arguments. We see here that the second argument is the base. When you see a function that has a named second argument, we always write the name, like you can call it this way. You can write down, I want the log of 10 with the base of 10. When you come back to that in 2 weeks, you'll know exactly what this function is meant to do. This is when you're using named arguments, this is how it looks in R. It's very similar to Python. This is a really good idea. It makes your code a little bit more self-documented. It makes it much easier when you come back later. You'll know what functions do. Okay, a few concepts. R is a programming language. You don't have to program very much to use R for statistical analysis. You mostly don't need to use control structures. Really what you need to do is apply a sequence of functions to data. So the parts of the programming language that you really need to know are variables, how to store them, data types, and data containers. And if you understand those things, those are the R language essentials that you need to understand data analysis in R. So we'll go through these three concepts: variables, data types, and data containers. And then we'll move on to some more demo. So variables in R. Let me not scroll too fast there. So variables are used to store values and to use them later. Common mistake is when you choose a variable name, try not to make it the name of a function that you want to use. It's true that R has different namespaces for functions and for variables, but that only helps most of the time, not all the time. It's possible to get into confusing points. So if you're going to make a list and you're going to use the list function to create it, don't store it in a variable called list. It causes problems. It's not good practice. You may occasionally try to use a variable name that is a reserved name. R will complain if you do that. If it says you can't use this as a variable name, it's because that's a reserved keyword. But for the most part, you'll be able to choose any name you want. Try not to overwrite functions you want to use. In R, there are multiple operators for assigning a value to a variable name. In Python, you'd always use the equal sign. I should point this out. When you're using named variables, it's always the equal sign. It's never any other operator. This is our argument. When you're using a named argument, it's always the equal sign. When you are assigning to a variable, you can use equals. You can also use this little arrow sign. This arrow sign is a holdover from a special keyboard that was manufactured in the 80s that used to have a button that had this arrow. It would type this arrow. It's that, I guess, tradition lives on in R and other languages that represent that arrow symbol as two characters. This is up to you. You can use whichever one works. Since they both work, oftentimes people use both of them. You'll probably see within single documents written by one person, they may use the arrows sometimes and equal signs other times. You just have to train your brain to see them as equivalent. This is an example of storing a value in a variable. I'm taking the value 20 and I'm putting it in a variable called width. When I run this and we have the environment tab open, we see that it goes right into memory. Notice that nothing prints out. R is pretty quiet in that way. Other programs might tell you, oh, I've created this variable, or there's some feedback. R doesn't give you feedback when you store variables. The only way to find out that it's there is to look in your environment tab or to print out your environment. If you want to check and see if it's still there, if you want to see its value, you can type its name and press return. R will print out the value stored in that variable. Variables can hold the results of computations. So I say that height is 5 times 9. See that it stores the result of that computation in the height variable. Now that I have variables, I can use them. I can perform operations with them as if they were the values that they are storing. So if I say width times height, it's the same as saying 20 times 45. You notice there was no variable assignment here, so nothing appears in the environment. It just prints the output. If you make a mistake, this is the command line way of looking at your environment is the list function. So I can list it. My environment is going to show all the things that are stored. It's going to show height and width. But I'm going to make a mistake and put in a variable with the wrong name and list it again. And so you'll see that the first time it's not there. Then I add it. And now I have this mistake. It's width instead of width. I wish I didn't do that. So now I can remove it. The function is rm. I can remove a mistake or a variable I no longer need from memory. That helps free up some RAM. Especially important when you're running in the cloud and you have limited RAM. So I can put things in memory, I can list them, and I can take them away. You'll use variables a lot. When you read in a data frame, you have to store it in a variable so that you can use it later. So that's probably one of your main ways of using variables, is when the result of any function that you want to be able to reference later needs to go into a variable. Data types. You can think of data types are a way to model the different kinds of data that we encounter every day. We know that you probably already intuitively understand the idea that there are different kinds of data. There are dates, they're different from numbers, and they're different from strings or names. R has this data type system, so you can model the type of data that you have. It's important that your data be represented by the correct R data type, because data type for R determines how R uses the values. We'll see that later in the linear regression example. By making something a factor, it completely changes how R treats that variable. There are a few common types. We have a numeric type for numeric values. That's integers and floats. There's Boolean values that holds true and false. In contrast to Python, true and false are in all caps. These are the designated keywords that represent true and false values. So all caps. There's a character type. This is really, should probably call this a string. It is a sequence of characters. R has a type called a factor that represents a categorical variable. So if your data value is going to be one of a small set of possible values, a factor is a good way to represent it. Things like grade level, level of education, gender, but not age, unless it's an age group, for instance. So factor is a type that represents categorical variables. R also has a concept of dates and date times. That's helpful if you want to represent a date. If you want to be able to do arithmetic using dates, you want to subtract two numbers and how many days are between them. Making sure that they're in the date time format first will let you do that kind of math that makes sense for dates. Some examples, I'm not going to run these, but these are, a numeric value, Boolean value. Just like in Python, strings can be in single or double quotes. You can, if you need to have a double quote inside, like if you wanted to If you need to have quotes inside of a string, then you can alternate the quote types, just like in Python. So this is still one string. The double quotes are part of that string. All right, data, like I said, data determines what you can do with the data. Data type determines what you can do with the data. So yes, I can multiply numbers. I can't multiply numbers in strings. R says, what are you trying to do here? I don't understand. Just a note, you can't add strings together like you can in Python. We do have a paste function that does that. There are some operators that do make sense for strings. For instance, strings have alphabetical order. So you can ask if strings are greater than or less than other strings, and that does work. Here's some examples with dates. The reason I'm using the term this day instead of today is because today is actually a function that we import later, and I don't want it to complain about function names matching variable names. The workshop is being recorded, and we will clean it up, and if the recording comes out well, we will distribute it. So some examples this day, there's 2 dates. Then I can compare them, and then I can, for instance, because it's a date, I can format it in a way that wouldn't make any sense if it was just a string. So I'll run those so you can see the results. These are the two dates represented. When I print them, they still look like the strings I put in. But you can tell that they're not actually just strings because I was able to reformat that string, that date, into a different representation, and it worked fine. So dates are pretty useful. So those are the data types you'll be likely to encounter. These 5. Where did I put them? Next idea, data containers. I'm going to just look at a few of them. Vectors there's a few types. Some types all hold the same kind of value, and some types of containers can hold multiple kinds of values. The one that you're going to use a lot is vectors. I'm going to skip over some of the materials. You could just come back and look at it afterwards, but vector is worth looking at now. We can make a vector using this C function. I don't know why it's called that, actually. I've always been a little curious. So we make a vector. I give it a list of values to put in the vector. It comes back with a vector. So here it is, my vector stored. It's a numeric vector. Our guess is the type based on the values we put in. It decided those were numeric. That's a good guess. For R, the first item is index 1. The last item is at whatever the length of the vector is. In this case, it's 7, and the last item is at index 7. So when I ask for item 1, the first item, it's going to give me 8. When I ask for the last item, it's going to give me 9. When I ask for 1, this is a way of specifying a range in R. One way of specifying a range. This is saying items 1 through 3. That will give me 1, 2, and 3. So in contrast to Python, R ranges are inclusive. This is probably one of the biggest things to keep in mind if you're coming from Python. I use Python every day and R about once a week. And this is something I have to constantly make sure I'm converting correctly when I go between projects. So this is how it works. Something to keep in mind. It makes a lot of sense if you're coming from some languages, and it's very confusing if you're coming from others. The reason vectors are important is that most of our functions, most our operations and functions will support vector input. So I can take a vector and I can square the vector, or I can add 2 vectors together, or I can multiply 2 vectors together. And it does pairwise operations. I didn't have to make a loop and go through each item in both lists and multiply the elements individually and put them in each vector. I didn't have to go through each vector item by item, multiply the items together, and then store the result in a new vector. I didn't have to go through all those steps. Instead, I can just say square this, and it works the way you'd expect. it's important. It's important that you keep in mind that vectors are supposed to be one type of value. And if you try to put multiple types of values into a vector, R doesn't complain. It just figures out something that will represent all those things. So if I try to put a string and a Boolean value and an integer into a vector together, it does it, but it turns them all into characters. It's probably not what I wanted or intended. It's important to, I mean, when you're using R, just keep in mind that it's going to auto convert things to do what you asked in the best way it can figure out how to accomplish what you asked it to do. It may not be what you want. Probably you didn't mean to make this all character, but here they are. They've all been stored as characters. Another example, these are integers with a Boolean. I can say, okay, go ahead and stick them in there. And it's going to say, oh, well, we'll make that numeric. that Boolean value is now numeric. This matters because here there's an isTrue function, and one is is true. Oh, it's probably all caps. There we go. This matters because one is not true in R the way it would be in Python. So this actually not only did it change the type, but it also evaluates differently. So keep in mind when you're making vectors, try not to make them mixed types. Otherwise, R will do something that you probably don't expect under the hood, and will convert the types for you. There are a ton of functions to make sequences in R. One of them, for example, this sequence function lets you make sequences that start at a value, go to another value, and take steps of some size. So for instance, I can say start at 1, go to 10, and steps of 1. You can also use an R shorthand. It says go from 1 to 10. The steps of 1 are implied in this case. I'm going to print both of these out and then store it so we can use that sequence in the next example. So there's our generating our sequences. This is what a vector of Boolean values look like. Boolean values are very important because we can use them for selecting subsets from our data frame. You want to say, I want all of the rows where something is true about the data set. That will give you a Boolean vector, and then you can use that to index. So for example, I'll take the sequence that I just generated and calculate all the ones that are even, because their mod 2 is 0. And that gives me a Boolean. It's the same length as my sequence, but now it's a Boolean vector of true and false values. I can use that to subset my sequence. So my original sequence was all the values from 1 to 10. When I said, give me that same sequence, but subset it based on my Boolean vector, then it pulls out just the ones that were even. You'll use this kind of subsetting a lot in R. I'm going to skip over matrix for now. You can come back and look at it later. Essentially, a vector. If you take a stack of values, you get a vector. If you stack up vectors, you get a matrix. And if you stack up matrices, then you get an array, a multi-dimensional array. This is a lot like NumPy's arrays, multi-dimensional arrays. Vectors and matrices you could use for data analysis. The multi-dimensional arrays, less used for data analysis, but pretty important for our programming. It's possible you might run into multi-dimensional arrays when you're doing some types of time series analysis. The other types of containers, aside from single type, are the mixed type. Two important ones are lists and data frames. Lists allow you to store mixed types. It's very common when you run a function in R, like a regression model. The thing you get back is a list-like object. It behaves like a list. And here's an example of creating a list. I say I'm going to make this thing called my list. It's going to be a list of 4 different things: a string, a date, an integer, and a vector. And when I run that, I did get, it stores in a different type. It says it's a data type, but this is my list. So list of 4 things: a character, a date, a number, and a numeric vector. Also prints it out here. So you can look at, if you need to get something out of a list, use double brackets. So if I want the first item, I use double square bracket 1. That'll give you the first item. I can combine subsets. So I can say I want the 4th item, but only the first 3 elements. So you can see those this pulls back the first item, and this pulls back the first 3 items from the 4th element. Not my favorite way to access lists. That's a lot of brackets, and I have to remember what I put in the list in the order I put it in. It's way easier if you use name lists. So here's another example. I can assign each thing to a keyword, same list, but now each thing has a name. Now when I store it, in addition to having an index, everything has a name. This makes it behave a lot like a Python dictionary. Here's my list 2. Now I have something called message, something called yesterday, something called with, something called my vector. When I want to access those items, I can now do it by name. I can say my list $, which says, give me, that's a symbol for element. So I say my list, give me the message out of my list is what this is telling me, or get me my vector and then give me the first 3 items in it. If you're not sure what the names are in a list and you don't see it in your environment, you want to find it in the environment tab. You can ask for the names of my list. This is a convenient way to get things. This is a convenient way to get an element out of a list. When you fit a regression model, there's like 20 or 30 list items. They all have names, things like residuals. And if you want to look at the residuals, you'll say my model $residuals to pull them out. Lastly, data frames. This is the kind of thing that you probably are familiar with if you used tabular data in any other program. It's the kind of data that would be in an Excel spreadsheet or a CSV file or in a pandas data frame if you're coming from pandas. There's a built-in structure that's data frame-like. It's called the data frame. That's the really common one. There are also 2 common variations you may encounter. One is called the data table. It's like a data frame, but it has large data features. So to make it more efficient dealing with very large data. You may also encounter a tibble, which is also a data frame-like structure. But it's used more for programming because it's more fussy about input and less helpful. So it's more likely to fail all the time rather than only fail under surprising circumstances. So these data frame, data table, tibble are all frame-like objects that you'll encounter. The syntax for making a data frame is very similar to making a named list. So I say I want a data frame. That's going to have an ID column, an age column, and a height column. And these are the values that you store there. The difference between a list and a data frame, though, is that these are all going to be the same length. So the ID column is the same length as the age column, same length as height. Pop that in there. Here's my DF showing up in the environment tab. I can see it has 3 variables, their types, and and some of their values. You can get the first row using the square bracket notation. So this is saying first row, comma, with nothing after it says every column. So I'm saying first row, every column. If I want just one column, I can summon it by name. So there's my first row. There's my first column values. If I want to make new columns in a data frame, I just declare them. So I'll make something called grade. I'm going to assign the value 3rd to it. This is going to take this single value and broadcast it to the whole column. We'll see the result of that. And then I'm going to take a subset of that column and assign it to 4th grade. So the first result, output, everything, the column was created. all the values are third. Jumping to data frame, to the second output, that subset I assigned to fourth grade, they all got that fourth grade value. Lots of functions operate on data frames. So for instance, a summary function, pretty good summaries for age and height, because those are both numeric. Pretty bad summary for grade. It just tells me if there's 9 values. If I make this just a little bit wider, then you'll be able to see that the class is character. So it's telling me you have 9 values of type character. The reason for that, that's a disappointing summary, because really we'd like to know how many third graders and how many fourth graders we have. The reason this is a disappointing summary is because of the data type. Really, instead of being a character, grade should be a factor. So I can say, oh, make this a factor, and then then produce the summary again. And when I do that, now instead of getting this unhelpful summary, I get the counts of the different levels of my factor. That's just one of the ways that data types really matters in R. When you load in a data frame, check the data types for all the columns. There's a few other functions. Like head shows you the beginning of a data frame. Tail shows you the bottom, the last few cases. There's, you can calculate the mean or the standard deviation of a column. These are the basic semantics of R. If you understand how to call a function, if you understand what lists and data frames are, you're going to be equipped to understand most of the examples that you encounter when you're looking for R help, and the ones we're going to look at right after this. So when you have questions about how a function works, use that help tab to look up the function and read about how it operates.